So I've just had a disconnection, and that may have reset everything. So let me go back and make sure that everything's working here. I'll have to redo all of this. So I'm in the process of designing the reverse bias LED amplifier using a program called Circuit Maker, and seeing if we can simulate the circuit before we actually build it. It would be nice because there's other parts of that circuit that are going to be built. There's an FET preamp that's supposed to be built. Then that goes into a couple of op amps which drive, you get a better signal because it's amplified. It's a very small signal. Like, we may be talking about microamps here. So now we've got a source. Let's go ahead and edit signal generator. The peak amplitude is going to be 1 millivolt. The frequency is going to be 1 kilohertz. There's no delay. It's going to be a sine wave. The magnitude again is 1 millivolt. Now we can do the analysis setup, do the AC, and then we're going to run from 100 hertz. Okay, let's see if it works. We have to save it. Let's see if it works. Okay, we've got 8 volts. That's DC, but where's my scope is not there. Oh, it's down here at the bottom. So there's no, it says 1 volt AC coming out of here. It should be 1 millivolt. Let's do the meter. Which I don't know where the meter is. Transient operating point. So 8 volts here. 16.05 nanovolts. 5 volts here. 0, 5, 8. So that's the resistance, that's the voltage across. No, that's 5 volts across the diode, reverse bias, isn't it? I'm measuring from ground. I've got a 5-volt difference between those 2 points. And there shouldn't be. There should be... It should be the same on both sides. You know, I don't know what they're using for a value for this. What we could do is we could... let's use this here. I'm going to delete that one. Oh, shit. I'm going to delete this one here. And that one. That looks weird. Okay. Now let's take a look. Okay, we've got something here. Now we've eliminated the whetstone bridge part. So I wonder if I can get a voltage drop. Oh, I've got no DC operating voltage. I'm reading transient analysis. That's just an AC voltage going through there. What is that reading? Picoamps? What's this picoamps? We need to add this guy to that guy. And then we need to add a meter. I don't know why that was there. And it goes to ground. So it says 5.02 volts there. So there's a problem. Oh, you know what? This is not what I'm supposed to do anyway. I'm supposed to have an LED on the other side with this. that's not going to work because I don't think you can connect. I don't think the circuit's going to know that that other LED's sitting there. Okay, aside from that, let's go back to what I was doing. It's because it's not connected, maybe. What? I can't connect it to ground. Well, that's another interesting point. So if that thing's going to pick off... Yeah, I just have to... I hate moving this file. Save file. Shit. Minus 5.912 microamps. Okay. Why? Let's try 1,000. Point. Okay, now it's down to 3 microamps. Let's try 3,000. One microamp. One microamp at 3,000. Okay. So that's what it says. So here, if this is 4.809 volts, I've got 8.509. So let me go to my handy dandy calculator. Uh-oh. There's an anomaly here. Oh, that's not right. Oh, I guess it is. There's just nothing written there. Let me go to my handy dandy calculator. I don't need this. I could just put calc here. We've got 8 point. Oh shit, that's microwatts. The fuck? How am I reading current? It's supposed to be 8 volts. What the hell is my, Okay, I've got to make an assumption here. I've got to assume that there's 7.2 volts across, no, 3.2 volts across the diode reverse bias. 7.1, no, 3.191. Go to the calculator. 3.191 volts. Divided by 1.016. Divided by 0.1016 equals 3 point, it's set in 3, it's like 3 meg ohms across that resistor. It's exactly so we go ahead, stop this, and we change this value. And then we change this one. This is going to be 3140748. That's going to be K. 3140748K. And now connect the lines. Like so. Let me save it. Now, theoretically, we should get a... I've got a better idea. Now, I want to read a voltage. Oh, I see what I'm doing. Now we're reading the voltage differential across the Whetstone Bridge. Okay. So we knew the value going through the LED was about 1 microamp. Theoretically, now maybe this might split it in half. Maybe. Let's see what happens here. I've got 8 volts there. I've got 4 volts here. 7.9 and 4.8. Well, that's not good. The voltage differential needs to be... It needs to be... Oh, that's because that's... Well, that's a voltage divider. What? Oh, you can click on the... You can click on the item and it tells you how much power it's using. Not that I want to do that. .8 volts. And I've got 8 volts over here. So it means that I need more current flowing in that other lead, that other section. What if I drop those down to 1 meg? And let's see, I should know how to do this, but it's just not on the top of my head. This is going to be a 1. This is going to be a 1. And this one, I'm just going to change this to 500. Okay, so that changed. Wait, what? 2.6. Alright, so we need to bring this value up, I think. Let's try 750. Okay. Okay. What about... We're running at 3 microamps, okay. .005. Okay, good, 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 okay. Let's try. So what we can do is we can use fixed resistors for the 2 top branches and a variable one at the bottom. We're getting closer. See, this one is still hanging out at 4.94. That one's 4.1. Okay. Oh, look at the voltage up there on the top. Minus 745 millivolts. Very, very, very interesting. Okay, let's see here. See, this is where I wish I could have a dial. Yep, that millivolts between the two of them is going down. What we're doing is we're actually trying to find the resistance of the diode while it's in a reverse bias mode. We have to manually go through all of this crap here. 1, 5. There might be a way to add a variable resistor, but I don't have time to look for that shit. I don't want to learn how to run the program. I want to run the program, you know? We're getting there. We got 4.93, 4.923, and 4.94 at 1.6 megohms. Now we've gone to the plus side. That's plus 95. And that's minus 17. So like it's a little bit more than 1600 ohms. Let me run this again. And now we've got okay. Okay, we're reading the microamps up at the top of the whetstone bridge. And the voltage, so the voltage difference, it doesn't matter what the voltage drop is across the LED, it's always going to run this particular current depending on those resistor values. We're using 1 mega ohm and we got 3 microamps. So it's definitely reverse bias. There is almost 5 volts between the battery and the resistor. So it's got to be 3 volts across that diode, which is less than the 5 volts. Or is it actually reading? Oh wait, hold the fort now. Wait just a minute now. Did that connect? Because I don't even know if it connected. Okay. File. Save. Probably don't even need that in there. So now we've got 4.94 and 4.893, which is okay. But here, because that's 0, so that's the voltage across the diode. That can't be the voltage across the resistor. So if we take this off, remove this, and then take this, go here, take this one, go here. Now we should read the voltage across the resistor. Aha! It's 3 volts. So that means that was the voltage across the diode. I'm just verifying my numbers, that's all I'm doing. It's close to that 5 volt range, right? But it's not like it's very strong. Like maybe I want a little more current going through there. So what if we do... Let's just try something and see what this thing says. I don't put a lot of faith in this, but it gives me a general, maybe it gives me a general idea, okay? Let's leave that as it is and see what happens here. I've got a difference of 1 volt between the 2 lines. Now it's reading 6 microamps. Yeah, that voltage difference. .7, okay. Does this go down? It does, doesn't it? That's 5 volts across the diode. Okay, I went too far. Okay. I wonder what that... Okay. I want to make a calculation. I'm going to go 1,000 divided by 1,600 equals, remember this number, 0.625. .588. So the ratio the ratio from the difference between the top and the bottom went from 0.625 to 0.588. And why I say that, that's just whether or not it's... I'd have to do piecewise approximation, do all these calculations, put it in the chart, and I don't have to mess with that to figure out if it's linear or non-linear or whatever. So that difference is 20 millivolts. So now we've got 5 volts across the diode, and it should be able to handle it. And we've got 6 microamps going through the diode, as a guess. So now when we take the next light source and send this light source to this diode, okay, so the question is going to be, so we're going to be looking at a voltage difference now instead of trying to measure current. So if the resistance changes, it's going to be in that depletion region. And so that's going to be your AC signal. The AC signal is going to come into that diode, and it's going to change that depletion region at the rate that the information's coming in. So it's not the light beam. It cannot be the light beam. It's the information on a light beam. Unless if you modulate the light beam itself, there's two things. Are you changing intensity? Because the intensity doesn't change. What if you've got this light beam at a certain intensity, okay, and then let's say, for example, you've got 20 millivolts. I could put a microammeter with a resistor. I don't want to do this. It's very sensitive stuff, this whole business. It just seems to me like it's the intensity change. So when the intensity changes on a regular LED, there's more current, which changes the value of the depletion region, which changes the resistance, yada, yada, yada. So if it works in the opposite direction, it's the same thing. If it collects light information, the phototransistor collects just the light information. But what about if there's something riding on the light beam? You know, what if you modulate if you if you modulate a light beam, it's like you're saying you're modulating the intensity of the light beam, and that's not what I want. That's not what I want. So I'm going to save this. We'll save, and then we're going to have to go to the website. Let me just go ahead and add this on here. Okay, let's go ahead and bring up the website. Let's edge somewhere. Modulating a Lightwave circuit, yada, 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 yada. That's just a sine wave generator. How to make an amplitude modulated wave. An acoustic absorber incident beam. Oh, what's this? Piezoelectric transducer generates sound waves. The piezoelectric transducer modulates the transmitted beam, but this is just not what I want. There's an LED with the waveform. You've got a FET here. P driver, yada yada. What is light source modulation? You've got your carrier. So you can do this with the FET. D diffraction pattern, modulated signal, voltage, deflected beam. Again, they're using the piezoelectric transducer with the aperture lens. Yada yada. Light modulation. Let's visit this web page. Are you a robot? Yes, I'm a robot. Thank you. No, take your garbage and you know where you can shove it, okay? Slit interference laser optical system. Slit interference. The near-field modulation of the light transmitted via these gratings is measured as a function of spatial frequency, and transmission gratings, the spatial resolution decreases as the spatial frequency increases. This is manifested in a deterioration of the light modulation as the spatial frequency increases. Caca. Near-field modulation signal in a weak interferometric domain arising from the interaction of laser illumination at a certain wavelength and a grating composed of 23 slits 100 micrometers wide. The J to X distance measured modulating I think it's using these slits to create this diffraction pattern, which is essentially a type of waveform, without doing it electronically. This is like a very narrow sine wave that's happening. They've got this actual distance in meters. It's got 0 to -2 and so on and so forth. So that's just using, like, if you've got this bunches of slits and whatever, and they're just, a certain distance apart and whatever, and okay, you've got this pulse, and the relative intensity is the same. That would be using the slit as a modulation source. Could you modulate the slit? If you put the piezoelectric transducer on the slit just shows, it could show a single waveform depending on what you're looking at. If you sent a signal on the slit and vibrated the slit at whatever frequency or whatever code you're trying to send it with, that might be a way of doing it. That's electrical to mechanical, which is a transducer. And you could do that with a 455 kilohertz for the ultrasonic. You can go through that whole range, moving the slit at an audio frequency. So the audio frequency, so that's, you can't move the mirror. You can't move any mirror. You can't move the grating. And so you have, when you do this interferometer thing, you've got the slit, right? So the light goes through the slit, and the reason for the slit is so that you can see spectral lines of things that you're looking at. So if you vibrate that, you are essentially vibrating the light going through the slit, right? That's interestingly cool. And that's the only way to do it. And that doesn't change the intensity of the light. It keeps it the same. But what about adding a signal to the light beam without changing the intensity to the light? So that's interesting. I should make a note of this. Let me bring up my my project notes. So this would be, I think this would be FM. This would be frequency modulation. The level of the 1 megahertz CW is going to be PW, or it's going to be FM, frequency modulated, question mark, or PWM. Don't think it is AM. No one's ever done this shit before. I guarantee it. Like, I'm the only person in the entire world that's doing this crap. I feel pretty damn good about that, you know? Okay, so... You see, when you put the amplifier on the slit, the slit itself has to be connected perpendicular. So you've got this flat surface that you've got this frequency vibration on, and the frequency vibration is going to be perpendicular to the surface. It's not going to be aligned with the surface. So the problem is going to be connecting the slit perpendicular to the axis of the wave that you're sending it on. That's doable, because you could make it metal. You could put the slit in a metal container type of thing, and then you could even use a magnet, and you could vibrate the magnet, because the magnet's a lot thicker, so that's going to dampen the waveform. You could make a slot that the slit fits into, and connect that slot to the amplifier, and then modulate that slot. Now, can you do it manually? I don't think you can do it manually, because it would be too wide across the spectrum, you know? That's the only way to modulate that light wave, is that slit. You can't use a circle. Now, what if you change the slit horizontal? If you change the slit horizontal and then put it flat on the surface, that's not going to work. It has to be vertical, and it's got to be perpendicular. You could change it. You could change the orientation of the slit, and then change the orientation of the transducer that's connected to it, and so you can vibrate that slit on any axis on that light wave. That's a really cool idea. You're hearing it here for the first time. Um, Now, according to that, it's like almost 2 hours into the signal. But if I do something here, yeah, I could actually do it over there. All right, so let me go back. Let me go and find. I want to find Audacity. And audio programs. So we're going to run Audacity. Now, this is going to be loud. It's not that loud. This is 20 hertz to 20 kilohertz. There's frequencies. Well, 15 kil. It's frequencies in there that you can't even hear. This is just a noise recording. In about 30 seconds, you're going to hear an anomalous noise that repeats a couple times. And that's not it. Shit, where the fuck is it? It's not here. Fuck. Yeah, here it is. Here's the anomalous noise. Okay. Now I'm going to give you this one here.
So there you go.
So there you go. That wasn't quite planned to get in there, but so there you go. And then what I wanted to do is actually, I'm going to remove this here so that I know when I go back to listen to the web page, my Twitch stream, that anomalous sound is there. And so it's up to you to decode that sound. And I will tell you right now that on both of those anomalous signals, there is information there. That's all I'm going to tell you. There is information in them sounds. And that's what we hope to find. So this is interesting. So they're doing something with the slit. They're doing their they've got a grating made from a metallic coating. It's 100 micrometers wide, separated by 100 micrometers, with n equals to 23, is illuminated with an expanded near Gaussian beam at 632 nm. The J to X distance is 1.5 centimeters. This grading to detector distance for the slit dimensions given, interference is rather weak and does not dominate the modulation of the signal. But it just gave me the idea of using, I'm going to be getting certain types of slits that has these little changes in them, but they're even across the band, they're not this small group of slits and that's it. That's what that deal is all about. So the whole idea is to vibrate that slit, we could use the 2D, the two slit thing, and so on and so forth. So you've got an input electrical current and output optical power. You get a laser diode, you've got a signal with an amp and a current that goes through an inductor and so on and so forth. I don't know exactly what that's all about. Let's check it out. Oh, we've got to bring up back edge here. So working on light modulation, etc. Oh, that's the same thing I just looked at. What the hell? You've got optical modulators. You've got optical pulses, amplitude modulation. Let's see what this circuit is here. Oh, this looks nice. Ah, okay. So here's a circuit. We've got a 741, some variable resistors. We've got capacitors, a bunch of resistors. There's a PNP transistor, which looks kind of weird up there. It's operated in a different type of a mode. And now you're transmitting, you're going from audio to LED. So we could take a picture of this. That's a crystal mic. I've got microphones. That's 2 batteries, I think. There's 2 batteries, 2 9-volt batteries up there. I don't know what that 2N3702 is. Then there's another set of 9-volt batteries over there. Well, that's quite a circuit, huh? Okay, let's take a picture of this. And so I will bring up my pictures. And we'll just open this with paint. And I'm going to copy that picture over. Like so. Okay. Let's file, save as JPG pictures. So this is going to be oopsie daisy, LW, LT mod 1 circuit. LT mod circuit 1. Now we could actually take a look at this web page. Visible light communications circuit using infrared. Okay, so you can use this simple visual light communication circuit to send audio and digital information through infrared light beyond a mile away with extreme precision. 5 milliwatts. Without a lens, the range is 40 feet. With 3 diameter optics or magnifying lens, the range can be increased to over a mile. Understanding the parameters is a photosensitive diode with a reaction time of a couple of nanoseconds. That's, yeah. It could be employed in the photoconductive mode, in which the amount of current passing through it depends on the incident light on it, or when used in the photovoltaic functionality, the voltage across it is dependent on light. So they're showing you two modes. One has a parallel resistor across of it, and the next one has a series resistor, 10K. It's actually a transistor which has a base current, etc. They're talking about different things here. I don't know about a pin diode. Like, it's an infrared diode. Transimpedance amplifier having extremely low input impedance, often known as a current to voltage converter. Due to their low input impedance load, these guarantee optimum current through a photodiode. They are able to offer a bandwidth of up to several hundred megahertz. Infrared is employed mainly because almost all red visible light LEDs don't find it easy to generate a 1/2 of a millivolt power, although numerous infrared LEDs possess an output of 10 milliwatts or higher. Collimate, the term is making it into a straight line. We know what collimation is. It's a collimated lens, which I don't have. Thermal noise. It's a nice little website here. "60 microvolts of noise and generates 3 millivolts of noise at the optical amp output," and so on. Pin diode features. Pin diode was decided as the better option as a detector in this project in the photoconductive mode, because they are not restricted by the gain and bandwidth like phototransistors. Pin diode provide us the unrestricted options for both above parameters, making it possible for us to develop personal amplifiers. Pin diodes are also extremely silent. Their noise is practically unreadable by equipment. Visible light communication is created using 3 circuit stages. The first stage is the FM transmitter, frequency modulation. The remaining 2 stages, the optical amp and FM demodulator, can make the receiver. My LEDs are going to be right next to each other, so we don't need to do that. An FM modulator is created to a, oh boy. Save image as LW mod 1B, no, circuit 1B. So you got your microphone. These are 3904s. I have those. So this is an FM circuit here. And upstairs we've got That's the modulation signal. Electret type, external audio sources used. Input should be a few millivolts, etc. Optical amplifier receiver circuit. Wow, that's a lot of shit. You could just put the signal into an FM. My radio has FM on it. Set it to a certain frequency. I could use the radio. There's no way I could build that and have it work. 80 kilohertz low pass, 40 kilohertz high pass. Optical amplifier stage. Figure 6 is to change the optical signal into an electrical signal. So it picks it up over here on the left. And to deliver a differential drive to the comparator. It's a whatchamacallit chip. Demodulator. CD4045. It's an FM demodulator. I don't really need that, because I got my radio. There's the amp with the gain of 200 for the speaker. I could come in useful. LW. Oh, he's even got printed circuit board layouts. Huh. I could make this with this layout right here. Huh. I gotta save this. Copy. Not that I would build this because, but he's got some interesting stuff here. IC3 is not an LM386 based amp, but rather some other IC which is obsolete now. Please adjust the amplifier section with an LM386 circuit by... Oh, they're talking about this one here, this IC3. Wow, let's get the layout and everything. This LC filter placed between the output of the optical amp and the FM demodulator can increase the usable distance by decreasing the bandwidth. Another circuit. receiver circuit. Now, this looks definitely a lot easier. I don't know what that 3702 is. That's a PNP transistor. Is that a photodiode? I think it's a phototransistor. Which I don't know if I have or not. That was interesting. Time is it? Quarter after? There's something here. What the fuck? Oh, it's this one. LED modulation circuit. Okay. File, save as. Mod circuit 2. That's a signal. That's probably an amplitude modulated. Is a summing amplifier where the signal input has a gain of -1, 12 volts flies amplified, yet apparent voltage turning LED to get into its linear range. The change in light output is then proportional to the signal voltage. The modulation of LED is one common way of getting a signal to a fiber. Yeah. So this one here changes the light intensity. Now, I could do that manually. I could just take a resistor, okay, and just move it back and forth at a lower frequency. But if I did it quick, I could simulate. I don't have to build that circuit. I can simulate that by changing the intensity. I just sneezed. So, I know how to do that now. I can do the transmitter. The LED intensity transmit portion, I can do that. And whether that affects the change in that whetstone bridge circuit or not remains to be seen. And that would be an amplitude, because that's an intensity change. And the other one was an FM. So we just need to get that in bias mode, reverse bias with those numbers, and then hook up another LED and just vary the intensity on the LED as a sine wave. Now that I know what happened, you know. So with that in mind, I'm going to take a quick little break and provide some wonderful music for everybody's musings. I know what my plan is, and I probably don't need the circuit program is gone, and this is gone. We're going to use 500K and 850, so remember that number. 500K, that's the receiver? Yeah, it's the receiver, nice. And that takes care of everything. And we're going to grab some music. And I'll be back in a bit. Let's see here. I wonder if my AFK thing is here. What's that say? Just like that. Oh yeah. Nobody's watching my stream like I really care. Alright, I'm gonna take a quick little brain break. Grab me a little food and do a few things. And we are gonna build up this circuit again for the third night in a row. And this time it better work. I wanna be an airborne ranger. I'm gonna live a life of danger. Give me some, yeah. Give me some. Gotta get some. Give me some. Oh man, I'm telling you. If I get it done this time, I think I might use a different setup. Freaking setup is just like right there. I don't like it. Yo, who got my cup, boy? Where the hell my cup, boy? Yo, it works. Yeehaw! I got my ice water bottle in a cup so that the moisture doesn't go all over my desk. You know what I mean? Jelly bean. You know what I mean? Burn. Burn. Oh, burn. You know what I'm talking about, burn. Lift that cap right off. Alright, time for us to get into the meat of the matter. You know what I'm saying, boy? 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 Oh my god, in heaven, I swear. Alright, let's get rid of this AFK sign. Now we want to look at the video capture. Then we don't want to look at a pyramid. And we'll probably get rid of the music. Like so. Alright, we're still streaming, right? Oh! Yeah, we is streaming, but I gotta fix my setup. Don't look quite just right here. Alright, that looks pretty good, I guess. Alright, so that's all working. I've got my cables. I lost my cable, boy. I can't find my cable, boy. I lost my cable, boy. I got no cable, boy. What am I gonna do, boy? Don't mind me. I'm just going Lulu. I'm spinning around in my chair right now. I think I find my cable, boy. I got my cable, boy. Alright, so I got some cables. We really, well, we don't need to actually do that unless if I could try to do it. But that poor voltmeter, I don't know, man. That's the only digital voltmeter I got up there. Alright, let's turn the scope on. We're gonna warm up the scope anyway. And we're gonna warm up this oscillator. As far as that digital voltmeter, I don't know. It'll read volts. It will read volts, but I don't know if I want to use it though. So, because what we're gonna do is we're gonna use a new battery connector, and we're gonna use this over here. I'm gonna use this setup. We're going. Oh, transistor is on this board, isn't it? Shit. There it is. Damn. Maybe it's okay, like maybe I can just move some shit, you know? Or just use it the way I got it, what the hell? I do wish I had a different battery connector thing though. I do have one. Oh, what's this here? Is it something I can use? It doesn't have the screws in it, no. I think it's some adapters in here. One of these has some screws in it, but it would be nice to find the one that's got the screws, you know? Oh, I think it's this one. Don't know. My toolbox. My screwdriver is missing. Send me down to Tucson in the morning. Uh-oh. Ow. I see a transistor. I see a LED. LED went poo-poo. Oh, damn. That's a small LED. Where the fuck is that box? What did I do with my toolbox, George? Oh, George, your toolbox is missing, George. What are you gonna do now, huh? Oh, it's this box right here. Why couldn't I use a laser instead of the other LED? I mean, it might be off key or something, but that's interesting. Bear with me while I attempt to grab a tool. Send me down to Tucson in the morning. Send me down to Tucson at night. Send me down to Tucson anytime you want. 'Cause when you do it, everything gon' be alright, right. Slop the toolbox on top of all my components. No, there's no screws in there. Fuck. See, some of these connectors have a screw in them, and you can use it to connect wires to. But these ones don't have it. Totally fucked. What about this here? I can connect a wire to this. Okay, what about the ground though? This'll work. Okay. There's a wire there, a center wire. And then we go from there. Let's have a ground wire. Might be able to connect the ground wire on the outside. No, I don't think that's long enough, is it? Oh, screw you, POS. Now I've got some wire here. Let's see. We're going to take this off and use this one for the signal, I think. No, I've got something. I've got something, by God. Okay. We've got a signal source. This is for the one of the modulation schemes. And I can check that by connecting it to the scope. My scope wires are currently connected. Let's take the scope wire and remove that. Let's go over here. The other one, which is the ground, is around this cap here, ain't it? Let's try. So 1K resistor. Okay, I've got the scope set up here. Now I need this one. The orange one is the ground, which is the yellow. Okay. Now our signal generator is connected to the scope. And that's at a very low value, so we're going to pump this volume up. Well, I don't want it up that high. What is that? 0.2? That's 200 millivolts. I'd like to get it down to that 100 millivolt scale. Oh God, okay, why is this not working? Orange is ground, yellow is ground. This is supposed to be ground over here. I shorted out my signal generator. Yellow. Damn you. No, I'm not going to use bad language. No, can't do it. You know? ground over here, yellow's ground over there. And this is my scope. I'm going to move this over here. Oh my god, what the fuck is wrong with this wire? Here we go again with these wires. Alright, now let's try this again. We're at 100 millivolts. We want a frequency of 1 kilohertz, and we are at something. Where's the scale? Frequency in hertz? Where the hell's the scale? A 100 times 10 is 1,000. So that's the scale. I don't know what happened here. I've got problems with my scope. I tried to clean it, you know. I know I cleaned the scope. I took it apart and cleaned it and sprayed it with contact sprayer and everything, and it's just not quite making the grade. I don't know why it's doing that. It's just jumping all over the place. I don't know if it's the scope or the generator. It's distorting and everything. Like, what the fuck? What is going on? My equipment's getting old to the point where it's becoming unusable. that's about 1 kilohertz. It's about 200 millivolts peak to peak. Alright? That's what that story is. And I'm just over here checking on everything, and everything looks abnormal, like normal. I wish I could use this breadboard, but we're not going to, so we're effed. Now the only thing I need the battery thing. I want to change the battery thing out. I don't know. I thought it was in there. It might be somewhere else. I guess we're just going to have to deal with it. So, if I want to look at the voltage, so that capacitor can just go fly. We've got the resistance across there. We've got our battery. What the fuck is this wire here? Okay, so what we want to do, what we're going to do is we're going to grab this yellow one, this red one. We're going to fire it up, and I don't know which way it goes, but process of elimination will tell me, I'm sure. Oh, what the hell did I do with the flashlight here? Alright, here we go. Alright, so don't go that way. It's not lighting up. Oh, because I got no battery connected. Alright, let's hook up the battery. I had the battery in backwards and it was lighting up. Alright, so we've got the LED, it's pretty darn bright. Let's see what kind of voltages we're talking about here. That's 1.85 volts there. Now if we go to our resistor, which I believe it's all set. voltage there, but there's no voltage. Alright, I got 3 volts across the diode. Okay. Oh, so we wanted to make the bridge circuit, didn't we? Shit. Oh, boy. Oh, what am I doing? Let's see, we have to do this different. I need another wire. This shouldn't be too hard to find. Okay, now I need that capacitor. I'm gonna put that little thing good in. That's a 4.7. And the minus is there. So let's go, the minus is here. Okay, we've got a capacitor in there. Well, monitoring the signal at the output of the oscillator. No, I guess I'm stealing some wire. Is there any wire in there? I can't see at all. I'm just a blur. This wire always used to strip easy, you know? And now it's just like fucking garbage. I cannot see at all. I just can't see. You know, I can't do this job anymore. I got that one. What about in here? I'm done with this green one. Green is signal. And a darker color would represent ground. Our oscillator is over here, which is this orange one. And the ground you're going to be a effing a-hole, right? I'm trying not to lose my composure, but you know what? Life happens. I deleted 2 of my streams because of it. At least I can see the damn holes to put the stuff in, you know? Ground is here. Now we're going to connect the oscillator to the capacitor. It is located here. And we may see a drop in signal, but we shouldn't. And the wire's fucked up. We'll try it again. So there's a little drop of a signal, but it's not too bad. I can't get the wire in the hole. It won't go in. Nope, there it goes. You gotta do it just right, you know? So there's a drop in the signal, and we could crank it up a little. So now we've got 200 millivolts is going into that diode. Now, I wonder, that's 1 kilohertz. We could slow the frequency down. And I can see it modulating. I can see the light modulating. So if we turn this off, you might be able to see it. If we even slow it down more. Yeah, right about there, it's kind of... You can barely see it now. You can see the light modulating, okay? But we don't really want that much of an intensity, you know? But it's okay. I mean, wait, let me go back and find out what that level was. Alright, I can see it modulating right there. And that level, it? 300 millivolts peak to peak, or thereabouts. And it's a low frequency, so I can actually see it modulating. So, now we know that that diode, we've got to change the oscilloscope to the other diode, and that's going to be the orange one, which is here. I'm going to remove this. The ground is connected, and it's still modulating. Okay, so good. This is the scope here. If I touch the lead, you can see it get bigger. And it's actually, so that's 60 hertz. I think that's 60 hertz right there. So now we're going to try to see without the scope probe. You could use a scope probe and try to check this LED out, but let's see what happens here. Okay, that just grounded it because that was on the other side of ground. Now that's on the other side of the LED. Now there's a signal there, but the only way I can find out if that's the same signal is to change it over here. No, my eyesight's fucked up. You can crank the level. Now the other problem is the bandpass of the we've got something, people. We've got modulation. It's very small, but it's there, and it's cranking though. That's with a high level, but I'm guessing that's changing the intensity. I don't know. Where's that going? Oh, it's going up, that's why. So now you can see the modulation on the scope. I don't know if you can see it or not. But what's happening is the AC ripple, which is prevalent everywhere, is grinding through that system. And right now I'm looking at a frequency of 2 kilohertz. 10 times 100 is 1 kilohertz. So there's the audio range. That's 2 kilohertz. That's 5 kilohertz. There's 10 kilohertz. So now, if I had a filter, if I had a high pass filter, I can get rid of the 60 hertz. We've got a modulated signal. But the intensity it does add intensity to the unit. see that the slow frequencies on that machine, it's better suited to like 1 kilohertz, which is fine. It adds glow to the diode. That's the signal that's writing. There's the signal right there. So I don't know if you can see it or not, but as I change the frequency, it changes the frequency that's writing on the 60 hertz. So it's like the 60 hertz is a carrier. Now see, this is something that they've been talking about, using the AC line frequency to receive signals in people's houses, but they'd still have to put some kind of an amplifier at the end of the AC line. Maybe they use a refrigerator, or the TV or something, and they can modulate sounds coming across that thing. They can demodulate it, and lo and behold, you got everybody listening to your shit, So, we've proven beyond a shadow of a doubt that in reverse bias, now we can adjust that resistor and find out if there's an effect change. So let's set this back to about 1K. It's kind of oh, something's really happened here. It's probably better on 2K maybe. Now I'm going to change the resistor. I'm going to max out the resistor. Okay, the resistor's maxed out. This is the resistor on the reverse bias diode. I'm going to see if we can get a gain on that signal. Yeah, so what it's doing, so actually the highest gain is at the highest resistance. So when the voltage drop increases across the diode, the signal actually goes down. It's shorting out the diode. It does lower the AC signal amount, but I don't care about that because we're just using wire ground, and I don't care about that floating AC. So if that's set to maximum, we can easily use a filter. Now let's see how high up it goes. Now we're going to test our response. So, alright, that's, what do we got here? So on a times, okay, so that's 1 kilohertz is 10. 1 kilohertz, 2 kilohertz, 5 kilohertz. We're at 10 kilohertz. We've got a signal. 20. So we're up to 300 kilohertz. Now we're going to go here. There should be a drop off. It's just starting to drop off. Alright, so that says 10,000. The fuck? That's 30, 50 kilohertz, 100 kilohertz, 500 kilohertz, 1 megahertz. We're at 3 megahertz. And all I really care about is 1 megahertz. This will go all the way up to 3 megahertz, as high as it goes. And I've got a signal here. It does start to go down around 3 megahertz. But at 1 megahertz, it's the same as it is the other levels. The other levels, maybe it's a little bit lower, you know. The 1 kilohertz, the audio range is a little bit lower, but it's there. Now, if I pull out the diode, wait, I've got a better idea. Something's happened. Something's happened. It's not coming from that diode. I'm going to pull out the lit diode. The signal's coming from somewhere else. It's probably coming across the ground. Yep. We got to find out if that diode's still alive. I took the diode right out and the signal's still there. So it's like that test didn't do anything, you know. Okay, now, I'm not seeing this thing lit up here. Oh, is it blown? That one's lit. I can't fucking tell which side is which on this stupid thing. I think the diode is blown because I can't get it to light up. You know what? The diode's gone. But the whole test was erroneous. Because the signal was coming across the ground line. I blew a diode. Let me try this yellow one. Wait, do I get another red one? That one's lit up. Let's try this white one. Got some infrared diodes here. But these won't light up. These won't light up, will they? We could go with the green. Alright, I just reverse biased that diode. God damn it, get in this fucking... Now the green one's lit. But the red flat one is not working. How about this one here? lost my patience doing this now. This whole project is just, it's killing me. That one's not working. Oh, it's working. This one's working here. That's the forward bias mode. So that means the arrow would have to be pointing in that direction. So if I put this over here like so. That resistor's all the way over. It's just a problem because the AC line's going through the damn diode. So the diode's like doing nothing. I can't confirm anything with the diode. So I've reverse biased the diode a couple times, and that one's still kicking. But this other one, I think this other one is dead, and I don't know why. But it's definitely gone. Can't even fucking tell which way it's going in there now. Oh my god, it's lit up. It's working. Maybe that depletion region needed to cool down. It was hot before because it's lit up too much, you know? So it is working. Okay, good. That's a good thing. I guess we're just testing diodes here. Yep, that one's good. And that one's good. This one, I think this is the dark one. This one's good. I don't know what the fuck this is. Alright, that's reversed. This one's working, but it's like really low. And that's not one of the ones that, my good ones work good. Let's see what we've got. We got some diodes over here, which I don't really know what to do with. What about this little dinky one here? It's not lit. That's not lit. Oh, that's lit. Yep, that one works. Okay. they're just, I'm not going to use these. Well, I can use them for some weird testing. Yep, that one's lit. These ones with these little clips on them, they don't have very good power. And that one's lit. Okay. Now the other thing is, okay, where is this dude here? Let's see. I got one more test to try. Alright, so that's lit in that direction. So that means that the arrow is pointing down. So for reverse bias, so if I want to do a reverse bias on this, if I want to do normal bias on this thing, I would point that to ground, which is here. Now that should be normal bias when I turn this on. And it didn't do shit. I'll turn it around. Is that my flat one? Try it again. Okay, that one's lighting up good. That's the normal bias right there. So now I can flip it around. And I know for a fact that it's in reverse bias mode. And the scope is monitoring that diode. And so what I'm going to do is I'm going to grab my mouse laser, which is really powerful. See my little Mauser laser? Pretty cool, huh? You know what's weird? I see one dot on the screen, but when I look at the camera, it sees some other weird shit. Alright, I'm going to point this laser right at that diode and see if something happens. Actually, let me, well, I'll just leave that on there. Fuck it. What the hell? Okay, so if I shake my hand up and down without the light on, nothing happens. Now let me take off this signal here so we can just look at that sine wave. Now I'm going to vibrate this light across this diode. The laser's affecting it, but it's, wow, it's really bright. And I didn't do the whetstone bridge thing. Now something's fucking up here. I've got a bad switch. If I do it sideways, nothing happens. I can see the entire waveform is moving. It's shifting when I put that laser light like that, you know. If it's back here, the intensity is not enough. Now let's try and change this value. No, it's not working. It's working, but it's just, I'm not happy with this here. Changing the value didn't do anything. It moves up and you know what seems to happen? It seems like if I move the laser light up and down, there's more of a response than if I do it across the diode. But the response is like, that's a 20 millivolt scale, 10 millivolt. The response is like 1 millivolt, well, maybe 2 millivolts, which is pretty good actually. So there's a 1 millivolt response across the laser, and if I change the current on that thing, it doesn't seem to matter, the voltage, because I can bring this down. You know what? I think there's more of a response with the resistor value all the way up. When you put more current through that reverse bias diode, the sensitivity goes down. So that would mean 3 microamps then, whatever that low value is, with a high value of resistance. That's 2.5 megohms. And I've got a response with a high-powered laser. But I can't do the modulation. I know there was modulation on that LED. The intensity of the modulation from the laser light did make a change, but that's not where I want to be. I kind of figured this would be the most difficult part of the project, because this is actually the most important part. This is where you take the light waves and you amplify them and you try to get the anomalous signals off of them. And I'm not able to do it because of I gotta build amplifiers. to build this low pass filter, the amplifier, the preamp. I'm not sure where to put that 60 hertz. Like, where is that even coming from? Is that coming from the scope? Oh, it's coming from the wire from the scope. So if I had a scope probe, which I do have, my probe is in here. You want to get probed? Would you like to get probed? No, I don't want to get probed. This thing's all fucking wired up to hell here. These probes are fucking expensive, man. Like, right now, they're probably like $250 or something. I got about 4 or 5 probes, scope probes. I've collected a lot of stuff over the years. And somebody's gonna get lucky and get it all. Because I'm just about done with this shit. Fucking cables. Jesus, I got so many cables. Alright, I'm gonna go pro now. I'm gonna take off the wire, the makeshift wire from the scope. Or not. Reconnect the scope up. It's supposed to be in 10 times mode, and I don't know exactly how that's done, but so we can ground this. This has to be grounded to the battery. I'm gonna need a ground wire for that somewhere. Oh, this is just garbage. Now we want to measure. Oh, that thing's still lit up, ain't it? Probably pull out that damn diode. Yeah, see, that's still the AC signal. What if I turn this on? It's still picking up the AC ripple. test the diode after I play with it in reverse bias mode. I can just flip it around and use that resistor to bring it back, and it works fine. I think it's too late for me to build this whetstone bridge. In fact, I know it is. So, I got a probe out here, which it helped a little, I think. But I've got to build a circuit that drops that AC hum. This bag's going to go in that closet. What else? You know, there's another thing, because this light bulb is kind of dirty. Okay, so I've been thinking about this this tune cavity, right? So there's the tune cavity that has to do with the Fabre Pro, whatever the heck it is. And so if I got some crystals, and so the crystals are going to be my test objects. And so when you put the LED, when you put the light on the crystal, if you put a laser light, on a crystal, what happens is it goes through the crystal and gets trapped inside. Now this is hollow inside. It's not like a crystal which is solid inside. This is hollow. And the light may work or not, I don't know. But this might make an interesting tuning cavity, This thing itself could be a tuning cavity, this thing here. So let's see what happens when I shine the laser light at it. And hopefully I don't get blinded by science, because shit does reflect. Now you can see on the camera, because I'm not looking at the item itself, there's reflections inside of it. If I look over, I can see light coming out of it, okay? There's definitely light coming out of it. But there's reflections inside of it if I move this light around. And that means that light is bouncing back and forth inside that thing. Now if I put it up close, it doesn't really matter that much, but still. It's an interesting idea of what light can do. And as a matter of fact, give me that light back. So I've got another laser here, which actually is a white light. Now let's see what happens when I put the white light up against it. Now is that just reflecting off the outside, or is it going on the inside? That baby's lighting up on the inside. Now if we clean this up more, maybe we can devise some kind of a test for that. Because that particular bulb, believe it or not, that's the largest hollow glass piece that I have. And there's some things that I have that may be secrets to the answer to my dream of communicating with beings from another dimension. Oh my. And nobody's, even the robots didn't come visit me to talk about stream poop. So that's it. I'm done with the stream. We need to build, I need to build a whetstone bridge. I need to build a preamp. I need to figure out I need to figure out how to get modulation into that diode. Or just skip that diode altogether and use we can use the solar panel. The solar panel works, you know. It works. I've got scraps of a solar panel somewhere. What else? The photo. So I gotta. So maybe what I do is I look for my photo transistors and my my photo diodes. I got two IR diodes in the little container here. Here's my little diode box here, which I probably should do something with. So I got a bunch of diodes. Got red, blue, green, and they're all tested. They all work now. The one that's in the thing here is reverse biasing. It works, but it's got AC hum on it, so that's not good. And the AC hum, you know, maybe there's got to be a way to measure that without. Actually, you know what there is. I was reading some millivolt level. I might be able to pick it up with this meter. Let's go ahead and find out. Why not? Because I am thinking about it. Alright, so like right now, it's all working. And all we gotta do is go to ground. We can take out this capacitor. Actually, that worked with that capacitor in there, didn't it? To modulate that, but that's okay. So ground is over on that side, and we want to measure on that side of the LED. So ground is here, and I go over here. What the fuck? It's lighting up the LED. Oh my god, it's light. Well, it's doing something to the LED. It's causing it to light up. It's causing it to forward bias the LED. Fuck. That's so weird. Ground across the LED. You know, it's doing something to the voltage across the LED, the meter. It's providing a continuity to it, or whatever the hell it wants to do, you know. I wanted to get a response, so maybe I need to get rid of this board. Well, no, this is a resistor. Maybe I don't need that resistor, you know. That's 2.5 megohms right there. And, well, I don't know if it works in a reverse bias, though. I haven't proven it yet. Because the signal was coming across somewhere else. Unless if I make my own generator. Wow. I could use a timer circuit and make a generator. And then the generator gets connected to the diode that transmits, and then the receiver diode. You know, I don't think it's gonna work. I don't think there's enough power there pick up a signal. It's got to be a photodiode. I gotta look through my stuff for the photodiode. I don't know about the phototransistor. I think, so maybe that's what I gotta do. I still got inductors to go through. I'm done. I'm done. I think it might be better. Like if I get to find the solar cells, find the photodiodes, find that other stuff, and I gotta make the circuits. Yep, I'm done.